All right. So moving on to 8.2, we'll talk about separation of variables. So we'll talk about some differential equations that are separable. So first order differential equations that are expressible in the form h of y, so some function of y, maybe it's like y squared plus e to the y or something like that, but some function of y times dy dx equals some function of x. These are said to be separable. And they're called separable because you can separate the variables, right? If you can write this as h of y dy dx equals g of x, then you can multiply by dx and call this h of y dy equals g of x dx. And then once the variables have been separated like this, you can go ahead and just integrate both sides in order to solve this differential equation. And of course, you're going to integrate the left side with respect to y and the right side with respect to x. So that's why these things are called separable. Let me give you a couple examples. So this first one says, solve the following initial value problems, and we'll look at a couple of those. So for the first one, we have dy dx equals negative 4x y squared, and then the initial condition is that y of 0 equals 1. So let's take a look. So we've got dy dx equals negative 4x y squared. So our strategy is to try to separate the variables, get all of our y's and our dy together on one side of the equation, and then get all of our x's and our dx together on the other side of the equation. So if I multiply through by dx, then obviously I'll have a negative 4x y squared dx on this side, which means I need to get rid of the y squared. So I'm going to go ahead and divide through by y squared as well, so that what I end up with looks like this. Dy over y squared equals negative 4x dx. And now I can go ahead and integrate that, right? So I can say, all right, so integral of 1 over y squared dy equals integral of negative 4x dx. Those are both pretty easy integrals to solve, okay? So we can say integral of 1 over y squared, that's y to the negative 2, so the integral would be negative y to the negative 1, right? So we would get negative 1 over y. And you might say plus c or something like that. Well, yeah, so maybe I'll call it, I'll say plus c1 equals, and then over here, what would we have? We would have negative 2x squared, right? So you'd have negative 2x squared plus c2. So we'll call it a different constant. Now our goal is to solve for y, of course. And so first of all, I can subtract this constant over to the other side and get a new constant value, which we'll just call c, right? So I'm just going to call this negative 1 over y equals negative 2x squared plus c, right? Some constant c. And I can get rid of the negative and call this 1 over y equals 2x squared. And once again, I mean, maybe this is I'm kind of abusing the notation, I guess, but I'm just going to call this plus c still. It's just some constant. It's not the same constant as the previous step, right? It's different by a sign, but whatever. I mean, it's just a constant value. And then finally, I can call this y equals 1 over 2x squared plus c, something like that. So the trick now is that I've got to solve for c. So I have to figure out what c is. And I can use this initial condition to do it, right? So I know that y of 0 should equal 1. So when I plug in 0 for x, or 0 for x, I should get 1 over 2 times 0 squared plus c, and that should equal 1. Well, this means that 1 over c equals 1, which means that c equals 1. Putting it all together then, we can say y equals 1 over 2x squared plus 1. And that's our solution. We can verify that this is a solution to the original differential equation. I'm not really interested in doing that at this particular moment, but you can check your work if you want. So that's that one. Give me a second. Okay, so the next one, we've got 4y minus cosine y dy dx minus 3x squared equals 0. So let's see if we can solve this initial condition problem. So again, my goal is to separate the variables. So I've got, this is part B that I'm working on. So maybe I'll do this. So I've got I can say 4y minus cosine y dy dx equals 3x squared, right? Just move the 3x squared over, and then multiply through by that dx, and I would have 4y minus cosine y dy equals 3x squared dx. And then once I've got that, I can go ahead and integrate both sides. And what do I get? So here I'm going to have a 2y squared minus sine y. And I'm not going to do the thing I did before and say, plus c1 equals, because at the end of the day, I'm just going to end up combining those constants. And so I'm just going to put the constant over here on this side. But this would be x cubed, and then we'll put the constant here, so plus c. Okay, goodness gracious, I've got to solve for y here. Oh, that's so nasty. I mean, I guess I don't have to solve for y. It's it's not going to be possible really for me to solve for y if I wanted to, but this is the solution to the differential equation. I could still at least solve for c, right? So I can use the fact that y of 0 equals 0 to solve for c. So I can say, well, since y of 0 equals 0, in other words, when x is 0, y is 0. So we're just going to plug in 0 everywhere. We would get 2 times 0 squared minus sine 0 equals 0 cubed plus c. Well, this is all just 0, right? We would get 0 equals c. Well, so that's kind of boring, right? So I guess what we end up with is this. We get 2y squared minus sine, let me try again, 2y squared minus sine y equals x cubed. And that's it. Goodness, it's easier to solve for x, actually. You could take the cubed root and say x equals the cubed root of 2y squared minus sine y. But anyway, in either case, right, that's the solution to the differential equation. Okay, let's do another type of problem. Okay, it's similar but not exactly the same as what we just did. So it says, find a curve in the xy plane that passes through 0, 3, and whose tangent line at a point xy has slope 2x over y squared. Okay. Well, this is a differential equation because if the slope is 2x over y squared, that's just dy dx, right? So dy dx equals 2x over y squared. Is it separable? Oh yeah, for sure. We can say y squared dy equals 2x dx. Okay, and then we can integrate both sides. And we get y cubed over 3 equals x squared plus c. Now, in order to solve for c, we need to use this initial condition. So we can say, well, it passes through the point 0, 3, so that means when x is 0, y is 3. So we'll say 3 cubed over 3 equals 0 squared plus c. Well, 3 cubed divided by 3 is 3 squared, which is 9. So we get 9 equals c. And that means y cubed over 3 equals x squared plus 9 is the solution to, it's the curve that we're looking for. Once again, I mean, we actually, this one we could solve for y pretty easily. If we multiply through by 3, we get y cubed equals 3x squared plus 27. And I kind of like that solution. But if we wanted to completely solve for y, then we could take the cube root and say y equals the cube root of 3x squared plus 27. And there's the curve that we're looking for. Okay, so this curve is definitely going to go through 0, 3. And the tangent line at any given point is going to be 2x over y squared. Okay, moving on. So, as we noted in the previous lecture, one of the uses of differential equations is that it helps us to model growth, exponential growth and decay. So here's how that works. Okay, a quantity y is said to have an exponential growth or decay model if it increases or decreases at a rate that is proportional to the amount of quantity present. Okay, give me a second. Okay. For exponential growth, so for exponential growth, dy dt, so the amount of growth of the quantity with respect to time, right? That's going to be proportional to the amount of quantity present, right? So it would have to equal k times y. If it's growing, k would be positive, right? For exponential decay, right, it's going to decay the amount present at any particular time is going to be proportional to the amount, or the rate of decay is going to be proportional to the amount present at any given time. But because it's decaying, this number would be negative, right? So again, k is positive, but this is a negative k. Anyway, so this value k is called the growth or decay constant, depending on if you're dealing with exponential growth or exponential decay. So you've dealt with exponential growth and decay before, but you've never probably seen it as a differential equation, but that's where it comes from, right? So probably in the past, you've seen the exponential growth model, you've seen the exponential decay model, but maybe you didn't understand where those things came from, or why they used the number e instead of the number 10 or something, right? Well, this is why. It's because the rate of change in the quantity is going to be proportional to the amount of quantity present, and that's what defines an exponential growth or decay model. And when you solve this differential equation, this is what you end up getting. So let's do that. Let's prove it. So let's solve dy dt equals ky. We'll just use a generic initial value, y of 0 equals y naught. Okay? So if dy dt equals ky, then dy over y would equal k times dt. And we can integrate both sides of this expression. And what we would end up with is ln of y equals k times t plus c. And if we wanted to solve for y, then we would exponentiate both sides, right? And we would get y equals e to the kt plus c. Okay, so to take care of this plus c business though, because this does not give us the model that we're looking for. I mean, it's mathematically equivalent, but let me come back to this top step actually. Oh, I see what I did. Okay, so hold on a second. So actually this step was correct. So let me start over, right? So ln y equals kt plus c, which implies that y equals e to the kt plus c. The c should have been in the exponent. Anyway, so this means that y equals e to the kt times e to the c power. And e to the c power, we'll just call that a different constant. We'll just call it c or whatever. Or, I don't know, if you like, we can call it c1. So we can say y equals c1 times e to the kt. Now we can solve for that constant using this initial condition, right? We can say, well, if y of 0 equals y 0, then y equals c1 times e to the k times 0 should equal y naught. Well, k times 0 is 0, e to the 0 is 1, and so this implies that c1 equals y naught. So putting it all together, we know that y equals c1, which is really y naught, e to the kt. And that's exactly the growth model that we expected to get, right? So if you're dealing with exponential growth, then this is the model that you use. If you're dealing with exponential decay, then this is the model you use. And let's look at an example. This is like an old algebra example, so you should know how to do these, but I just want to refresh your memory. So this is according to the U.S. Census Bureau, the world population at the beginning of 2014 was about 7.1 billion and growing at a rate of about 1.08% per year. Assuming an exponential growth model, estimate the world population at the beginning of the year 2030. Okay. So we're going to use our exponential growth model, y equals y naught e to the kt. We'll take 2014 to be year 0 or time 0. So at t equals 0, so y naught is going to be 7.1 billion. Okay. 1.08% is the growth rate, k. We'll change that into a decimal, so that's going to be 0.0108. And then t is going to be the amount of time that passes from 2014 to 2030, which I suppose is 16 years. So then the prediction would be this. We would say y equals y naught e to the k times t, which we said from 2014 to 2030 would be 16 years. And let's see. (7.1) times e to the 0.0108 times 16 is 8.4-ish. So this comes out to about 8.4. Right? This is what my calculator is getting. 8.4. So so there will be about 8.4 billion people. In 2030. Okay, so that's that. Another thing to remind you of is about doubling time and half-life, right? So if y grows exponentially, then the time required for the original size to double is called the doubling time. If y decays exponentially, then the time required for the original size to reduce by half is called the half-life. So for example, let's use the information in example 4 to find the doubling time of the world population, right? So how long would it take for the population of the world to double from 7.1 billion in 2014? Well, so if the initial amount is going to be 7.1 billion, it actually doesn't even matter what the initial amount is, because the final amount is going to be twice as much as it. So in other words, if we're dealing with this growth model, and we just leave this as y naught, this has to be 2 times y naught because it's doubled, right? So 2 times y naught equals y naught e to the kt. And actually, we know what k is, and so we can solve for t. But notice that the y naughts will cancel now. So 2 equals e to the k, which is 1.08% times t. And then we just need to solve for t. So natural log of 2 equals 0.0108 t. And that means that t equals ln of 2 over 0.0108, which is approximately, let's see, ln of 2 divided by 0.0108 is about 64. It's about 64 years. So if our initial year, I guess, was 2014, then 2014 plus 64 is 2078. So we would expect the population to be 14.2 billion in the year 2078. That's probably not actually going to happen because the population growth is not constant. It's slowing down, which is good because our planet probably couldn't hold. Well, I mean, 14.2 billion people it could probably hold, but there's an upper limit, right? There's a threshold that we can't really cross, just in terms of resources and stuff. Okay, last one. So this will be an exponential decay half-life type of situation. It says, if 100 grams of radioactive carbon-14 are stored in a cave for 1,000 years, how many grams will be left at that time? And radioactive carbon-14, by the way, has a half-life of about 5,730 years. So let's see if we can figure that out. Well, so again, I'm going to use my decay model, y equals y naught e to the negative kt. And it almost doesn't matter that it's 100 grams that we begin with, because we're going to be left with half that amount. So you could put y naught here and then 1/2 y naught there. Since they gave us the 100 grams, I mean, I guess we'll use it. Half of 100 is 50, so we can say 50 equals 100 times e to the negative kt. We know that t is 1,000. Oh, but I'm trying to use my prediction already. Okay, well, so this isn't going to, because we need to solve for k first, right? Well, we can do that, right? We can do that because we know that the half-life of carbon-14 is 5,730 years, so we can plug that in for t and then solve for k. All right, so we'll say 50 equals 100 times e to the negative k times t. In other words, 1/2 equals e to the negative 5,730 k. We can take the natural log of both sides. By the way, this is ln of 1 minus ln of 2, which is just 0 minus ln of 2, so this is just negative ln of 2. I guess the other way to see that is this is ln of 2 to the negative 1, and then you can use the power rule and call it negative ln of 2, which is kind of nice because then that'll cancel that negative there. So I can say ln of 2 equals 5,730k, and then I can divide by the 5,730. So k is ln of 2 divided by 5,730. Okay, cool. So now I can use this. Now I can use this k to make my prediction. I can say, all right. So what's the amount going to be after 1,000 years? What's the amount y going to be? Well, I'm starting with 100 grams. I'm going to have negative ln 2 divided by 5,730 times t, which is 1,000 years. So now I can pop all that into my calculator ever so carefully. I'm going to have 100 times e to the negative ln of 2 divided by 5,730 times 1,000. Ooh, my calculator does a very nice job of converting that, but it's approximately 88.6. So approximately 88.6 grams will be left over after 1,000 years. That makes some sense, right? Because half of it to disappear would take like almost 6,000 years. So after just 1,000 years, you'd expect well more than half of this to be left over, right? So we started with 100 grams, you're left with 88.6. That lines up with what we would expect. Okay, and that's it. That's all I have to say about separation of variables.